Hello world, it's RationalPi, and I'm with you here today with potentially a working traveling salesman problem prototype. I ran it a few times and it seems to do what it is we're looking for. So we're going to try to see if we can reproduce some of my results here today and kind of show you what different amount of nodes can do in terms of time complexity. So over to the right you see a flowchart with my code, and we actually just got to reuse my MBA conferences code up until a certain point, of course. So we basically do the same exact thing up until we generate the node number list. So let's go ahead and jump right down to there. All of this is the same. You've seen it all before. You see me generate the paths. You've seen me make the path in the city data structures. But here's where things get different. So what the permutation algorithm that I found was actually from a gentleman off of Stack Overflow, but it needs numbers. So, and it also assumes that these numbers are already sorted going into the sorting algorithm, or the permutation algorithm. So we're going to go ahead and abide by those rules. I could probably change it to where it can be any specific number, but just for ease and just for convenience sake, we're going to go ahead and just assume they're in order. And really, since we get to decide the names and the node numbers of each, then we can go ahead and do that ourselves, so it doesn't really matter. So we create this X array of integers, and let's say if we have 5 nodes, it's just going to end up being 1, 2, 3, 4, 5, and that's what this loop right here does. It generates a list of 1, 2, 3, 4, 5, where we have 10 nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. These console.write lines are just for a formatting sake. And then we have the path equals total path cost, where we send in the array and we send in the MBA paths array. So this is where things, we created a new method, and that's going to be down here, the total path cost. And let's go ahead and switch over to the total path cost flowchart, and this one's pretty easy. We're going to go ahead and create, or we're going to initialize the total path cost, which is right here, pretty simple, set it to 0. And then we're going to, for each set of 2, which basically means length minus 1, because if we have 5 nodes, we want to find 4 total connections, or 4 total paths, because it goes 1 to 2, 2 to 3, 3 to 4, 4 to 5, that's 4 paths. And then we're going to do another loop, which then analyzes every set of, or every path available to us, which is why we need the MBA paths array. And then we say, we have this big long expression here which says if the first node of the path that we're looking at is equal to a node that is in our array, or, which is these 2 parallel lines here, or it's equal to the second node of the same path and the next node, so let's say this was node 1, this is node 2 over here. If node 2 is found within either the first node or the second node, then we add the path cost of that specific path with those specific nodes to the total path cost. And that's going to happen for 2 to 3, 3 to 4, 4 to 5. So in total, there's going to be 4 additions to the path cost, which is exactly what we wanted it to do. So awesome, fantastic. So now we have our total path cost of the original permutation of our 5 nodes. We're just going to assume it's 5 nodes, just for convenience sake in this example. So then we're going to go back up here. Now we have our first total path cost. And then we're going to go ahead and set this first path cost to the shortest path, because technically it is, because it's the only one, right? Pretty simple. Okay, so let's go back to our flowchart. So we generate our first path cost, we set it to the shortest path, and now we're going to get down to the permutation algorithm. So that's right here. So while it's true, and you'll see why it's either true or false in a second. So while the next permutation is true, let's go ahead and jump to that, shall we? TSP Permutation. So this one's a little bit more involved. So the print array is pretty simple. You just basically write it to the console. I didn't feel like redoing that every single time, so I went ahead and made a print array method here. So the next permutation algorithm is from Sani Hutunin on Stack Overflow, and then we're going to initialize our first desired index. And now again, this assumes that the list is in order when you send it in. So for the first n-2 values, because you'll see why in a second, we're going to compare a value to its neighbor value to the right, and if it's less than that, and let's say we have x equals 1, 2, 3, 4, 5, I will be then set as 3 because its length, which is 5 minus 2 is 3. 3 is, of course, less than equal or less than 4, so that's true. And then we set our first desired index to I, which is 3. Okay, great. And then we are going to, and then if we find out that there's no indices that its neighbor is greater than that, then we know we've reached our last permutation. So the very last permutation is going to end up being 5, 4, 3, 2, 1, which makes sense because it's the exact opposite of our original permutation. So then we're going to set our second desired index to -1, or just to initialize it really. And then I is going to start at 4, which is going to be n minus 1 this time. And then we're going to compare the value at the index that we found before to the index of the new value of I, which is 4, which is, so originally the largest index, or the first desired index, was 3. So that x at 3 is equal to 4. And then the x at 4, I here, is less than 5, so that's true. And it may not make a whole lot of sense the way I'm explaining it, but if you follow the flowchart, it's going to explain it very well. And then we're going to set the second index, our second desired index, to that I value. So what effectively this is going to do is now we've obtained 4 and 5. That's what we want. The value at index 3, because it goes 0, 1, 2, 3, 4. We have the value at index 3 and the value at index 4, which is going to be the first two that we're going to analyze, because those are going to be the first two that we're going to want to switch when we find our next permutation. And then we're going to want to change the third value, move it to the end, and then analyze those last 3 numbers, then the last 4 numbers, then all 5 numbers. And it's just going to keep doing that over and over and over again until we end up with 5, 4, 3, 2, 1. Makes sense? Clear as mud? Fantastic. So let's go ahead and set a temporary variable to that first index, to the value of the first index we wanted, which is 4, which is the next to last one. And then we're going to set the first index to the second index, so we're basically switching 4 with 5. So x of 3 is now equal to 5. And then we're going to set that last index, or largest index 2, to 4. So then we flip to 5 and 4. So now our array is 1, 2, 3, 5, 4, which is the next natural permutation. And when we're trying to find all the different permutations of 1, 2, 3, 4, 5, the first inclination is to switch those last 2. So then the next time it goes through, it's going to change that third one and the last one. And then it's going to change the last 2 again. And then it's going to go back and do the next one. And it's going to go through those last 3 again. And so on and so forth. This last for loop is just to reconfigure the actual array. And then you're going to return true because there is a next permutation. And you're going to keep doing the next permutation, the next permutation, the next permutation, until you get to that 5, 4, 3, 2, 1, where the preceding number is always going to be greater than the number next to it. And then you're going to return false. And that's when you're going to break that original loop. So let's go back to the original loop. So while permutation is true, which is what this is saying right here, because while is expecting a true or false statement within the parentheses. So while there's a true statement for next permutation, the path is going to be equal to 0. We're going to find the next path of the next permutation because it changes that x value, or the x array, and it's going to have a new path for us every single time. And then if we find that the new path is less than the shortest path that we already have saved, then we're going to set the shortest path equal to that path. And then we're going to write it out to our console, and then we're going to print the array to let everybody know, hey, we found this shortest path, and then it's basically going to update the user. And then we're going to go down and decide that the shortest path is shortest path, which means the very last shortest path that we find is in fact the shortest path of the whole system. So let's start putting some numbers to this pretty face that we've developed here. And if you have any questions or concerns or any questions of the method, please do comment below. I want this to be as clear as I possibly can make it. And when it gets to sorting, it's really tough to put into words. You just gotta do it. So let's go ahead and do it! So let's start it up. See if we can get it to work. Alright, so this is what pops up. Let's see, number of cities. We want to do, let's do 5 cities, right? So name the city of node 1. Let's name it A. We can do 1, 1, B, 5, 5, C, 30, 30, And this is longitude, latitude, just like we did with the NBA. D, let's do 2, 2, so we can have some change up there. E, let's do 7 and 7. So then it finds that there's 4 updates to the current shortest path, and then we find that the shortest path is 41, so let's do some checkups. So we decided it was 1, 4, 2, 5, 3. So let's see, 1 to 4, oh, we don't have that information, I forgot, I nixed that out of the code. But anyway, I did do some previous testing, and it does add up to that proper amount. I could go back and I could add in all the prints of all the path information, but that's just going to take some time, and I don't want to waste your time. But just trust me, it does add up properly. Addition is something that computers can do very well. So we found the shortest path between the 5 nodes. So I went ahead and did this for several different nodes, and these are the results I got, without getting too crazy in terms of time. So went up until 8 nodes, it really did it in less than a second. But when I got to 9 nodes, it jumped to 2 seconds for it to process. When I got to 10 nodes, it took 20 seconds, which is about what we want it to be, because 9 factorial, and then if you want to go to 10 factorial, all you got to do is multiply 9 factorial times 10, which is exactly what we want it to be. However, when I went to 11 nodes, it ended up being 14.25 times 10 nodes, which equals about 4 minutes and 45 seconds. So I haven't gone past 11 nodes yet. I would assume 12 nodes would be roughly around 15 times that amount, so roughly an hour and 5 minutes or so. I can do those if you'd like, so we can get some more data. And what that means is my computer, when it's running a piece of code that I develop in Visual Studio, it only runs at about 0.01% of my total CPU usage, because my CPU only runs at 4% based on Visual Studio. So Visual Studio only actually uses 4% of my total computing power. But then, even when it uses maximum computing power, because I have other things running, it still is only available to it only a fraction of a percent of what total I have theoretically, which theoretically I should have 29.7 GFlops. And realistically, I'm getting about 5 megaflops, which is not great. So it may just be my computer being a piece of crap, or it may just be a memory issue that I'm having, or it could be a wide variety of things. But, you know, that's not bad. We got a working prototype for the traveling salesman problem. If we threw in there 100 nodes, it would work. It would just take forever, literally forever, probably the age of the universe long forever. So I might do a couple, I might go up to 13 nodes, see how long that takes, and I'll report that back to you in a video comment. So I'm going to go ahead and end that video with you here today. If you liked the video, press the like button, share it with friends, share it with people that might be interested in coding, leave a comment. It really does help the channel out, and I will see you guys in the next video. Have a great day.